Okay, so well, let me begin by thanking the organizers for putting this program together and for having me here. So it's a pleasure to be back to the ICTS. Last time I was here was right before COVID, and it's a great program too. I'm going to be mentioning it during my lecture today. So many of these terms you have already heard before. Generalized hydrodynamics, local prethermalization. So I'm going to introduce this hydrodynamization term, which maybe is new to you. So this is the outline of the talk. So split in three parts. So it's an introduction, discuss more or less, the basis of the topics we are going to be addressing. And then after it, we can have a small discussion. Then I'm going to have another part, which is discussion of an experiment with cold atoms and those experiments that have contact interactions. So that's the feature about all these experiments that are done in here. And then again, we can have a discussion after that. And then I will go on to discuss experiments that have contact interaction and dipolar interaction. So that's the plan for the talk. So let me first start by telling you a bit about what is the setup that I have in mind for those experiments and the theory that I'm going to be doing. Okay, so these are ultra cold gases experiments, and all of them all around the world begin with the creation of a Bose-Einstein condensate. And that was first done in 1995, and that was the Nobel Prize in 2001. So this is showing what happens with the momentum distribution or the velocity distribution of a Bose gas when you cool it down to near 0 Kelvin, so you get Bose-Einstein condensation. So they start with that. They create a very cold Bose-Einstein condensate, and then they load them in optical lattices. And what that allows them is to create different geometries. They can create one dimension, which is what we are going to be interested in today, 2 dimensions, and also 3-dimensional lattice. Now, once you have those gases in the lattices, you can do many things. You can study quantum phases, and that's what I started doing as a graduate student. Shortly after, I realized that what I wanted to actually do is to study quantum dynamics. So that's another thing you can do with those cold gases. And nowadays, people are using them for quantum computing. So that's another big thing. And this shows a 1-dimensional geometry and a 3-dimensional geometry. So what happens when you get these very cold atoms in 1 dimension? Well, they are very cold, and they are bosons. I'm going to be having in mind bosons in this talk. So what happens is that in 1 dimension, they interact by a contact interaction. Okay, so you see it in here, and important in the experiments is that they can control that contact interaction. Now they have 2 ways to control that contact interaction. They can control, this is the scattering length in 3 dimensions. They can control that with Feshbach resonances. But the other way they can control the contact interaction is by changing the confinement in the transverse direction, which for them is just a matter of, like cranking up the power of the lasers that create the lattice. Okay, so these are the ways. And when you have bosons in 1 dimension interacting with contact interactions, you heard about them yesterday. So they are essentially modeled by the Liebling model, where this is the contact. And since the experiments can change this G to make it very large, they can also reach the regime. You can think of this as being infinite, and that's the Thom-Girardot, what is called the Thom-Girardot regime, in which you can map bosons to fermions. So you see in real space, right, the contact interaction is infinity, so you cannot put the bosons on top of each other. So they, in real space, behave as fermions. Is there a question? Okay. So this was first realized at Penn State in the lab of Dave Weiss. You're going to be hearing that name a lot. So he realized for the first time the Thom-Girardot regime, and he actually explored the equilibrium properties of those 1D gases. Okay, so what I'm showing you here is a plot from this paper in which they measure what is called this G2 local correlator. Okay, and what is showing here is the experimental results. So you see there are the points with the error bars. which they can do using photo association. And the line is the prediction of the Lieb-Lineker model. Okay, so that shows that in those experiments, right, you get a very close realization from that model, and you can use the Lieb-Lineker gas to describe the equilibrium properties. Photo association, so they can use light to photo associate, and then whether you have photo association or not depends on this overlap. So that's the way they did the measurements. So this is exciting, but a really exciting thing happened 1 year later, right? When they took these 1D gases far from equilibrium. So what they did is, and I'm going to be discussing that protocol a bit later. So what they did is they applied laser pulses, okay, to take the gas very far from equilibrium, and they created like an initial bosonic distribution function that has, like, let's say 3 peaks in momentum space. Okay, so you think of the Bose-Einstein condensate, I showed you the plot, right? So in momentum space, you have the occupation is very sharp. So in 1 dimension, you cannot have Bose-Einstein condensation, but this can be still very sharp. And when they apply the laser pulses, they get a distribution like this, where this is 2 times h k, where this k is the k of the laser. So they started with this distribution, okay, and then let the system evolve. Now think of what is happening physically here, right? So you have a Bose gas in a trap, right? And then you have bosons at 0 momentum, and then you have a bunch of bosons at finite momentum, right? They are all overlapping. And then what's going to happen, the ones that are moving fast will try to go out, right? But there is a trap, and they will come back and so on. And after some time, they found that the bosonic distribution function, it equilibrated to something like, looks like that. Now they put a lot of energy in the gas. So if this would have been a thermal equilibrium state, you would have expected to have something that is Gaussian like this dashed line. And you see in the experiment, they changed this gamma, right? That's this dimensional parameter that parameterizes the ground state and thermodynamics of the Lieb-Lineker model, which is the ratio of this G1D and the density. As a function of this gamma, they actually never saw thermalization. Okay, so that was very exciting. About 20 years ago, it's kind of difficult for us now to think about that time in which we didn't know what was happening, because at that point, we didn't know whether the fact that they were seeing equilibration was because of the experimental imperfections, right? This was supposed to be an isolated system and closely described by an integrable theory. So at that time, a lot of people thought that there shouldn't be any equilibration at all, that this should go forever, the motion should go forever. So that was one of the questions. And the other question was, I mean, is there a way to describe this distribution that they got after equilibration? Okay, so that was about the time that we got interested on these problems. And later, then a lot of work was also done in 1 dimension, but not in this setup, but on atom chips. Now, the difference between atom chips and this setup is that in atom chips, you get very weak interactions. Okay, it's a different regime of the Lieb-Lineker model. Is this gamma much smaller than 1? So in these experiments, you see that you can have it 1 or larger. Good. So that's the experimental breakthrough, if you want, like 20 years ago, and we started thinking about how to understand what happened in there, which led to this generalized Gibbs ensemble. Now, I'm going to be showing you throughout this talk a lot of results, and those results are really exact calculation. Let me just spend a couple of slides telling you how these exact calculations are done so that you see what is behind them. So what I'm going to be modeling is the infinite repulsion limit in this Thomson-Girardot regime of the Lieb-Lineker model. But on top of that, I'm going to put it on a lattice so that you have bosons hopping on a lattice. And then we have, in general, an external potential, which in the experiments is like a Gaussian trap that keeps the bosons from flying apart. Now, this looks like a non-interacting model, but it's actually interacting because the bosonic operator satisfies this constraint. Okay, you cannot put more than 1 boson on a lattice side. Okay, so this means that you cannot really solve this as a non-interacting theory, but what you can do is map bosons to spin and then you can map a spin to fermion through the Jordan-Wigner transformation, and this model is free, right? So what that tells you is all the thermodynamics of this model can be described using a non-interacting Fermi gas. Okay, so diagonal operators, like things that depend on the density, can be described with fermions, but one particle correlations, things like experimentally relevant, like momentum distribution function, are very different from the fermions, right? So just think of this momentum distribution function now for the hardcore boson gas in the ground state, right? It's going to be very peak, right? The ground state of Fermi C, right, of a Fermi gas is going to be a Fermi C. So if you have homogeneous system, the bosons will look like this, and the fermion will look like this, okay? So very different. So this is where the work is, on computing those correlation functions. So how is it that you see? So that's where they work. And the other thing that you get from this mapping is that you see the occupation of these fermionic eigenstates, right? Since they are non-interacting, they are, no matter the dynamics that you have, they are going to be conserved, okay? And these are the quantities, the conserved quantities that we are going to be using related to what Ben was saying yesterday. So if you want to think of these in Ben's language, these were the occupation of the theta's that he had for the Liebig-Linear gas. Okay, so I'm gonna come back to this point. But where is the work goes is in computing these correlation functions, because you see when you map bosons to fermions or spins to fermions, you see that you get these strings in there. Now the way this is usually done, right, is using topless determinants. Okay, topless determinants have very nice asymptotic properties that you can get analytic expressions out of them. So the way we are doing this is different. We are going to be using properties of Slater determinants, and you will see where the advantage comes from computationally. So, and we can study this correlation function both in equilibrium and far from equilibrium, right? So remember, so the fermions are essentially, if you are in the ground state, it's a Fermi C, it's a Slater determinant, and one can compute the unitary evolution using Slater determinant properties. Is going to be, a new Slater determinant with prefactors that coefficients that depend on time. And then you can just take this expression, plug it in here, and using properties of Slater determinant, you can write this equal time Green's function as a determinant of a product of matrices. Okay, so if you look at the algebra that you have to do in here, right, you have something that the computation time scales with the square of the system size and this summing here. So if you were to use topless determinants, the computation time will be L to the 5. Okay, so in this approach, why it's very useful is like if you have a dilute system, and you will see why dilute systems are important, and this gives you a humongous advantage to get the asymptotic expansion and so on. Okay, so this is what's behind all these results I'm going to be showing you for hardcore bosons, right? It's an exact calculation. There is no molecular dynamics simulation. It's just an exact calculation of the time evolution. Good. So once we had this, then we started thinking about the dynamics. So now we can just theoretically, right? Let's forget about the experiments. There were discussions about experimental imperfection and whether this is the reason for equilibration. We can just take experimentally, let's say, a Bose gas, a Thomson-Girardot gas in a box, right? Sort of the Gedanken experiment we talk about in our statistical mechanics classes, right? So you take the gas in a box and open it into a bigger box, right? And the question is what happens, right? So we tell that in regular gas, what will happen is, well, it will expand, the density will become homogeneous, and the velocity distribution is going to be described by Maxwell boundary distribution. So this is what we're going to be looking at here. So I'm going to let the gas expand, and we'll look at the momentum distribution function. Okay. Good. So this is what happened in this Bose gas, mappable to free fermions evolving unitarily. Okay. And on top of that, only few bosons. Okay, of the order of 10 bosons. in here. So that's another thing that you want to keep in mind in the context of the discussion yesterday, whether you need very large number of bosons. So you see that after some time, right, the density becomes homogeneous. So you see they are happening. This is in some time scale of the Hopin amplitude. You see that the density becomes homogeneous and the momentum distribution of the bosons stops changing in time. Okay, so isolated, integrable, the momentum distribution function equilibrates. Okay, so it reaches state, the wave function is still evolving unitarily, but the momentum distribution and the density distribution are not changing. Okay, that's what we call equilibration. That's what Ben was calling yesterday relaxation. Okay, so now if you look at this one, you could not tell, is this equilibrium a thermal equilibrium or not? So you have to prepare a very atypical state to see that this is not thermal equilibrium. So this atypical state is actually similar in spirit to the one that I have in the experiment. So what I prepare is the ground state in the presence of a lattice, and I'm going to turn off the lattice. So this is what happens. Okay, so remember, I started with a lattice potential, like the one the experimentalists had, and then I turn it off. So this is evolving under a homogeneous Hamiltonian in epochs. Right, so you see the density is kind of oscillating, but this oscillation actually, this you can describe also with free fermions, and you can analytically show that these oscillations decay to zero polynomial in time. But really the amazing thing is what is happening in the momentum distribution function, right? So you see that after some time, so let's wait for it to start, it just evolved into something that has equilibrated. You see it in here, right? So these very sharp peaks are indication of the zero temperature of the initial state. And then if you wait, right, for some time again in the units of the Hopin, you get something that is completely equilibrated. Now, why is this momentum distribution function surprising? Right? Imagine if someone comes in a statistical mechanics lecture and tells you, okay, the equilibrium distribution of the gas in here looks like that, right? So there is no potential in there, right? And instead of having just one peak, you have these 4 peaks, right? That without doing any calculation, you know that this cannot possibly be thermal equilibrium. Okay? Good. So then that already addresses that question as to whether the experiments were getting equilibration because of imperfection. Actually, we can do an exact unitary evolution and we get equilibration. So this is something that doesn't depend on whether the system is coupled to a bath or to some external agents. It happens under unitary evolution. Now the next question then is, can we describe, right, that momentum distribution function after equilibration? Right? Can we predict what it is, knowing what the initial state is? Okay.
So the entire system evolves unitarily and the thermalization is subsystem. So how do I reconcile that fact?
Right. It's not true that it's only for the subsystem.
I see.
Okay, so you could, because you're thinking about the subsystem about being something local, right, in space, and then that's the usual way. But you could also think, like expand that view and think of my subsystem in here is the one particle sector, right? These are n particles, right? And then the other particle sector, right? The other, they act like a bath. And then it's not local. And it better be like that, because in the experiments, that's what they're measuring. Okay, that momentum distribution function of the entire system.
Thank you.
Good. Other questions about this? Good. So then we know that it equilibrates. So that's now beyond questioning here. So, and now we want to see to what it equilibrates. So you can do the calculation for what happens in thermal equilibrium, right? And this is like a generalization of that idea of Slater determinants to final temperature, right? And now if you are you have a system in thermal equilibrium, and let's say in the grand canonical ensemble, right? You have two parameters that you have to fit, right? Your chemical potential and your temperature, and you can fit those knowing the energy and the number of particles in the evolving state, right? So those ones are conserved during the unitary evolution, and you can then just use them to fit the chemical potential and the temperature. If you do that for the box case that I showed you in there, so these are the kind of results you get. So the time evolution, this is the zero momentum occupation, right? So this is, I just take the occupation of this zero momentum state, right? And I plot it as a function of time. So this is the time evolution. This is what you saw, right? So there was a very sharp peak. There was some, oscillation, and then flat. Now, if you look at thermal equilibrium, you see that is different from that. Now comes the other thing that, I mean, it was very surprising to me at the time, is how about the effect of the number of particles? Right? In the experiments in those gases, they have, between 10 and 200, right? So then you can ask yourself, well, what happens if you change the number of particles? So, and this is what is shown in here. So what is shown in here are the state after relaxation. If I just take the system and double its size, right? You have to keep, densities constant and so on. So when you are taking the limits, right? So it's like, if I start with 15 particles, right? I expand in some box, and then to study 30 particles, I double the size of the box and double the size of the other box. Okay, so that the density after equilibration is the same, and the density before in the initial state is also the same. And what you see in here is that if you go after the system relaxes, you see that the momentum distribution function, right, for 30 and 15 particles are really indistinguishable from each other at the level of these plots. And if you look at the thermal equilibrium prediction, well, the two are indistinguishable from each other in this plot, and they are different from each other. Okay, so if I would have only shown you 15 particles, you could have said like, well, but maybe, right, if you increase the system size, one goes to the other. That's not the case in here. Even for this number of particles, you get something that on this scale is indistinguishable. Okay, so now then the question is, how do we describe this momentum distribution function? And then, of course, and it was mentioned yesterday, you can think about this ensemble being the maximal entropy ensemble given these two constraints. And I was telling you that in the case of these hardcore bosons, we have all these occupation, right, that are conserved. These are, again, the f of theta that you were hearing about yesterday. So, well, we now want to maximize the entropy conserving these quantities. Okay, so if you do that, then, well, you have to write a generalized Gibbs ensemble, where now the number of terms in this case scales with the number of lattice sites in your system, right? So if you go to the thermodynamic limit, then you have infinite conserved quantities. Now, if you are dealing with thermal equilibrium, I told you, you have to use the energy and the number of particles to fit the chemical potential and the temperature, right? And this is done numerically. For this system, the great advantage that we have is that once you know, right, the occupation of these conserved quantities in the initial state, you can get the Lagrange multipliers analytically. Okay, I mean, imagine having to fit numerically like something that is infinite, right? So, and now then we have really the Lagrange multipliers are determined by the initial occupations, right? We can plug it on the generalized Gibbs and then do the same thermal equilibrium calculation, or like the same equilibrium calculation, not thermal, but now generalized thermal equilibrium. So if you do that, then you get a perfect agreement. So this is the zero momentum occupation, and here you have the momentum distribution function from the GGE, and after relaxation, and you see that they are on top of each other. Okay, so even for this small number of particles, right, it works incredibly well. Now this is also amazing, right, because the time evolving system is isolated. If you want, right, that there are no energy fluctuation, no particle number fluctuation. And in this state and in this state, there are particle number fluctuation and energy fluctuation. All we are conserving is the average. Okay, so you would think that to describe it, you would need a microcanonical ensemble because you have a very small number of particles, but that's not the case. You can use a perfectly well-defined grand canonical ensemble to describe this. So that essentially settles those two questions, is that indeed equilibration occurs under unitary dynamics, and in integrable systems we have an ensemble that allows to describe observables after equilibration. Yeah, question.
Hello. Yeah. So this relaxation is in the momentum space, but even if the numerics that you showed, in the dense, like in the real space, things are not still oscillating.
Yeah, but what I was telling you is that in the real space, remember the real space density, these are like free fermions. So there the equilibration is slower, but it goes also to the homogeneous case, as a power law. So it will go flat, and of course the ensemble will describe it, okay? Mm-hmm. And it also describes, of course, the other case with the multiple peaks. So this was initial momentum distribution function, and this is after equilibration. So good. So I actually gave a full pedagogical talk on that meeting in the 2019 about this topic. I mean, you probably can find it to see the entire discussion. So this generalized Gibbs ensemble we heard yesterday. I'm going to go quickly through this because everything we've seen is behind this generalized hydrodynamics description, because essentially now, instead of having those fluid cells thermalized, well, we have them generalized thermalized, and then the underlying description is a GG. Okay, so this all you heard yesterday. So now I'm going to be showing you results from GHD. There is an extra piece that it was not in yesterday's talk. So you saw this part in that pedagogical talk. So in the experiments, there is this trapping potential, and we are going to be like doing generalized hydrodynamics in the presence of the trapping potential. So you get this extra term. And then once you know, well, and you heard yesterday that what this B effective is. So it's a function of this rapidity distribution. So and once you get it, then you can get densities of conserved quantities, which you heard. And I'm going to be showing you results for like the sum of the interaction plus kinetic energy, interaction energies, and actually rapidity distribution. So that's it. So let me, instead of spending time there, tell you about hydrodynamization. Okay, hydrodynamization is a term that comes actually from heavy ion collision, high energy, ultra relativistic heavy ion collisions. And this is a question about this hydrodynamization that I was asked since started talking about thermalization in the early 2000s. So people in the heavy ion community didn't know where very special time scale shows up. So let me just tell you about these heavy ion collisions, right? So you get these ultra relativistic heavy ions, right? So if they would be at rest, we think about the nucleus as a sphere, okay? So, but they are ultra relativistic, right? So if you are in the lab frame, you get the Lorentz contraction. So instead of having two spheres that are going to collide, you have two sheets, right? And these are ultra relativistic, so they are really compressed. So in the lab frame, what happens is that they have these ions that come against each other. These are like two sheets, right? And they collide, okay? That's what is shown in here. And then when they collide, right, so what happens is you get some remnants that are moving away, and in between those remnants, you get a quark gluon plasma. Okay, and the amazing thing is that in those experiments, they find, I mean, in the modeling of those experiments, they find that, well, they don't know what happens right after the collision, right? There is some quantum dynamics in there, but after 1 femtometer divided by Z, they can use hydrodynamics to describe what happens. Okay, so, and the big question there is, where does that time scale come from? Okay, and now, interestingly enough, working with the coldest matter in the universe, these cold atoms, we can potentially say something about this hottest matter in the universe. So that's something I'm going to be telling. But this is what is called hydrodynamization. So after this time scale, hydrodynamics describe the system. So that's why they call it hydrodynamization, which is not to be confused with hydronization, which is when the hydrons form and then they have other dynamics. Okay, so hydronamization, very short time scale. So that's another thing that we're going to be discussing, which is now related to very short dynamics. Good. Any question about all this background in there?
This last picture, isn't it just the collision time?
No, we're going to see the collision time is much shorter. It's like a tenth of this. Okay, this is past the collision. Remember, these are very, I'm going to show you the scale for that. So it's 10 times higher. Okay, other questions? Right. I mean, so which relation? So you're talking about this? Yeah, here. Right. So in all this, indeed, I mean, you could start with the ground state, but remember that after you do a quench, right, like in this case, right, in the final Hamiltonian, your initial state will not be in the ground state. Okay, so even if you start with the ground state of the gas in the small box, when you open into the bigger box, that's an excited state. So, and then that's true. And the same happens when you put the lattice, right? It's the ground state, you remove it, it's a highly excited state. So you are always going to be at some final temperature and some density. Right? If you are in the ground state, nothing happens. Right? There is not going to be any dynamics.
Hello. Yeah. Does the relaxation of the Tonks-Girardeau gas happen in like a much longer time scale than the ideal Bose gas, or is it the same?
The equilibration time, right? The equilibration time depends. This is a very important question, and it's the kind of question that we break our minds with. The equilibration time is not something that only depends on whether the gas is weakly interacting, strongly interacting. It depends strongly on the initial state. Okay, so you can see it. I think that experiment helps a lot, like the one I was showing with the box. So because you see, if you have, right, so look at this. So you have here a box with the gas, right? You let it expand. Really, it doesn't matter whether this gas is strongly interacting or weakly interacting. It cannot possibly relax before this has hit the wall and come back. So you see immediately there is a time scale there that is set by the size of the system. So it always depends on the initial state. Okay. Now, if you set similar states and so on, then you can start talking about whether the times are different. But the initial state is essential for talking about relaxation times. Okay.
About GG, is there equivalent?
Yes, we look at, you mean whether there is a microcanonical version of the G? Yeah, we looked at it and there is equivalence. That's right. Right. There is a microcanonical GG. We wrote like a paper about it. That's right. Indeed, and it's not trivial, right? That you can have an ensemble in which you have this infinite concept quantity. And in particular, also here, the concept quantity are not even these local quantities, right? That one thinks of. These are the occupation of those rapidity modes. Well, I mean, immediately you see that you need the time to get to the edge of the box. That already is a time that is scaled with the size of the box. Like, I mean, like maybe 2 or 3 times that time. In this case, okay, yes, that's right. Good.
Maybe slightly tangential. So is there some GG version of ETH as well?
Yes, there is a GG version. And I mean, I think we discussed those. This is a very interesting, it's in that pedagogical talk I gave like 6 years ago. But there is a generalized version of ETH for integrable models. So essentially, and the idea is actually behind the answers to the idea is that all eigenstates with similar distribution of conserved quantity will have similar expectation values of local observable. Okay,
Thank you.
So Okay, good. So then now that we know all this, we actually set up.
Excuse me.
Oh, sorry, there's another.
Sorry. So one comment. So
Yes.
the first day I gave a talk related to this problem, and since this is the first day of the conference, many of you guys are not here.
About which problem? This
But
problem?
this case. What way I discussed was the shape of this initial configuration fixed some time scale, and if this is flatter, the decay is later. There's some power law decay will can be seen, and this power is completely fixed by the shape of this tip of this.
So this shape that you're thinking of, this shape
Yeah.
in position space?
In
Okay.
momentum space.
Exactly.
In
But this I'm showing in position space. Actually.
Oh, I see. So in moment, yeah. So
Okay, so this is different. You see, the point is that you could have, I think that's what you probably had in mind, right? You in this problem, we have this in position space, and we have, let's say, like in the box, we have this in momentum space, right?
Yeah.
You could have, right, and that's the problem probably you had in mind, you can have this in position space and still this in momentum space, and then this will fully determine the dynamic. But
yeah.
not in this case.
Yeah,
And that's
yeah,
why I was
yeah,
saying that
yeah.
the initial state is very important.
Yeah. So
Okay.
yes, and this shape of this in momentum space.
That's right. But if it is homogeneous in real
yeah.
space, right? But this is not this case. Okay,
Yeah.
good. Good. So then now I told you the experiments, right? They motivated, right? They motivated, this understanding. They saw that there was no thermalization. They also saw that you could describe the equilibrium properties using the Lieb-Liniger models. But I mean, recently there's been a big development actually in the field, and it has to do with this measurement of rapidity distribution. So this was actually something I was thinking about as a graduate student, and the question that I was trying to understand was like, at the time, people were doing a lot of time of flight experiments, so to measure momentum distribution function of the Bose gas, right? So you turn everything, let it expand. So the question that I started to thinking about was, well, what if you let them expand in one dimension without turning off interactions, right? That was the problem and this is what I'm going to show you, and you see that connects to this asymptotic rapidity. So what I'm going to show you now is what happened with the Bose gas that is trapped, and you let it expand. Now, this in here is the momentum distribution function of that Bose gas, and this is the underlying distribution of the fermionic description. Okay, this is the Fermi C. The reason this is not a Fermi C as the one you are used to, like a block, is because the system is inhomogeneous, okay, because there is a trap. So now let me show you what happens. And it's not only important that it happens, but also in the time that it happens, right? In experiments, the time matters. So this is what happens as the gas expands. So as the gas expands in real space, right, the momentum distribution function of the bosons very quickly becomes identical to the momentum distribution of the underlying fermions. Okay, and all you need to do is wait about 2 to 3 times the expansion of the initial size, and you get this distribution of the fermions. So what does that tell you? That you take these Bose gases, let them expand, right, in 1D under their own interactions, right? You will be able to measure, if you measure the momentum distribution function of the bosons, you will be measuring the rapidity distribution. Okay? So that's what we learned from there. And it took a bit of time. And you see, that was 2005. And in 2020, with Dave Wise, actually the lab is in the basement under my office, they actually managed to do that experimentally. So what that means is experimental challenge, right? Because you need to make sure that the expansion happens free, so that there are no potentials as the boson expand. And this is what they got in the experiment. So as a function of time, you see that you get the momentum distribution function going from something very big to something like what I showed you there. Now, we know, right, in the experiment, let me just so you have an idea, there are of the order of 10,000 one-dimensional gases, and we know the distribution of atoms in those gases. So we did the theoretical calculation of the momentum distribution function. At long time, it's perfect match with the experiment, not at short times. And to understand the difference, you need to know that the experiments, they don't measure momentum distribution function, okay? They infer momentum distribution function from position measurements after time of flight. So what that means is that this discrepancy could be due to the fact of an imperfect time of flight. So, I asked the experiments, can you expand longer? And it's like, no, the gas hit the bottom of my chamber. So then as theorists, then we had to actually model what happens in 3 dimensions after they turn off the lattices, which we can do because we know all correlators, right? And then we did the modeling, and you see it's nearly a perfect match with the experiment. So you're seeing here at different times, experiment and theory are on top of each other. Now, the only discrepancy still remains at time at T0, and the reason is that we are doing 0 temperature ground state theory, and they have a real gas, which is slightly high temperature. But you see how close it is to 0 temperature that one can describe everything. And then you can collect the largest 3 times in here and put them together with the fermionic momentum distribution function. And then you see that they are measuring the rapidity distribution. They are measuring the distribution, the momentum distribution of the underlying fermions. Okay, so it's pretty amazing, right? So if you take an experimentalist and you take a Fermi gas and a Bose gas and let them both expand, measure momentum, they will not be able to tell the difference between the two. Okay, the distribution after expansion will be the same. So good. So once you have that, then you can use it in different models, and there are actually been studies of different models. Sutherland studied the inverse square pair potential, the continuum TG gas. We actually studied the attractive Fermi-Hubbard model, in which actually related to discussions yesterday, you have to start worrying about bound states and impenetrable SUN fermions and so on. So this is something that is general for integrable models, and it's being already implemented in other groups. So Ben Leff and Stanford already measured that. Isabel and have also done the measurement. This is in atom chip, okay? And then there are also measurements in the group of Christoph-Nagel in okay, so, and probably there will be others. But now this momentum, this rapidity distribution can be measured in the experiments. So good. So once you have that, when we had that, we said like, okay, let's then look at benchmarking generalized hydrodynamics and breaking it. And this is work that we did also in collaboration with Jerome a few years ago. So what is the idea here? So the experimentalists, they get their Bose gas very close to the ground state, and then they can do a very strong quench of the harmonic confinement or of the Gaussian trap. And by that, it means for them just increasing the power of the lasers that they have in there, okay? So that create this trap. So this is now the evolution, right, of this rapidity distribution when they do a 100-fold increase of the confining potential. So, and you see what happens. So you see this time 0 is narrow, right? Now, when you do that quench, you put a lot of energy into the system, right? Because it's trap energy, the gas starts to compress. So, and that's why as you put this trap energy becomes interaction plus kinetic energy, the rapidity distribution broadens, and then you get the oscillations, right? Now, in those gases, there are of the order of 10 to 50 particles, right, per tube, right? And then you say like, well, is generalized hydrodynamics justified? No. Can you use it? Yes. And if you blink in there, I actually now put already the generalized hydrodynamic results on top of the experiment. So look, these are the experiments, and these are the experiments with the generalized hydrodynamics. So the blue curve are generalized hydrodynamics, and to see that there are 2 different curves in here, you have to focus on this difference. So generalized hydrodynamics is incredibly accurate, even though there are few particles and you can do humongous quench in those systems. So with that, those profiles, you can then calculate, right, what is the sum of the interaction plus kinetic energy, which oscillates in here and during the first two oscillation periods, and you see the experiment and the theory are on top of each other. And you can go to very large, like long times, right? Like these are of the order of 60 milliseconds, and still at least this energy is described by this. Now, this doesn't tell the entire story, because you may say like, well, but really there is nothing happening. I mean, this is like a smooth thing. Actually, there is a lot of stuff happening with the quasi-particles, right? Because think about this, right? So you start with something that is very dilute, right? And then you compress it, it goes to high density, right? So if you go to high density, effective gamma, it changes a lot. And to see this, what we did is compute these kinetic energies and the interaction energy. So you see, this is what happened to the kinetic energy as you go in the quench. And you see there is a big drop of the kinetic energy at the maximal compression point, right? Because at that point, that energy becomes interaction energy. So you see there is something abrupt happening in here, which is well described by the experiment, by the theory too. So they see it in the experiment and it's well described by the theory. Okay, good. So this was the kind of the long time of the contact interaction, right? So then we decided, let's try to understand, right? For example, in this quantum Newton's cradle setup, what happens before generalized hydrodynamics becomes valid, right? So there were these questions yesterday, right? So you do something to the system, you will be able to use generalized hydrodynamics at some point, right? But you need some local equilibration. And this led to some really amazing surprises. Yeah? So now you see there is again a quench, right? But notice that the quench now is not in the trapping potential, but the quench is adding a lattice, right? This is a short distance oscillation. So this is something that you cannot describe with generalized hydrodynamics. Okay? And the question is, what happens when you do that? So we take the gas and take it far from equilibrium. Now let me try to give you a picture of what is happening in the gas, okay? So that you see what the time scales are. So initially, right, we have one peak before the quench, and after the quench, we have these three peaks, right? And then we let time run. Now, what is going to happen, right, after you created that state? Again, as I mentioned before, so there will be some dynamics at short times much shorter than the scale of oscillation in the trap. But then on the time scale of the oscillation in the trap, those particles that have very high momentum will try to leave the trap, right? But what happens to those high momentum particles as they try to leave the trap? Their momenta decreases because they are climbing a hill. And that's this last plot. You see, this is 1.5 milliseconds, okay? That's why there is this slowdown. Everything I'm going to be telling you next is much shorter time scale when those particles are all in there, okay? It's a much shorter time scale than the time scale of the trap and the time scale of generalized hydrodynamics and so on. So this was what the first thing that the experimentalists got, and it's amazing how much stuff is in these plots that look noisy. Okay, so look at the things that you can immediately get from this plot. First, there are some very fast oscillations. Okay, you see in there are very fast oscillations. Those are real. It's not just noise. So the other thing is that you see that there is a time scale that is longer at low momentum than at high momentum. So we can do the simulation, right, the calculation for one gas, and then it's all much clearer, right? So you see this longer time scale at low momentum and shorter at high momentum and the oscillations. So that's one thing that came out of the experiments. The other thing is that if you look at the energy that you deposit in different momentum groups, right? Again, in here, you see the momentum group, and this is the log of the energy. You see that the groups around one, there is a very fast increase in the energy. In the experiments, it's hard to see, but it's there. So if you look at the theory, it's much clearer, right? So there is a very fast transfer of energy from the high momentum, okay, to this intermediate moment. And that's what we want to understand. And actually, it's not apparent in this plot, but there are two time scales that are playing a role in there. Good. So let's try to understand the time scales. And to understand this, right, I'm going to step back and simplify the system completely. So I'm going to remove the trap. I'm going to remove the quench. And the way we are going to think about this is we're going to have a homogeneous system, and we are going to apply a Bragg pulse within this Raman-Nath regime. Everything that you need to know about the Bragg pulse is inside the area of the pulse. So the length, the height doesn't matter, it's all about the area. So, okay, and if you wanna like check that this makes sense, I mean, here we describe all the glory details that homogeneous system with this pulse describe exactly what happens in the homogeneous one with the real pulse. So initially, now we have homogeneous systems, so we have a Fermi sea. Okay, after the pulse, you see what you have. You have a superposition, right, of the initial Fermi sea and then higher momentum peaks that come with an amplitude, right, which actually I see that this should be the same functions. So that are determined by the modified Bessel functions. And this B, which is the A in here, is the area of the pulse. Okay, so right, if you want to forget about the equation, what does that tell you? It tells you that the occupation, right, of these higher momentum peaks is determined by the area, by that area of the pulse. Okay, so and now if you have this state, you can immediately realize that there are two time scales. So let me plot this scale now for your benefit here in the, so what is that state? So, right, you have the initial Fermi sea, you have the copies, right? This is this 2h bar k, right, that you have in there, right? And for the Bragg pulses that they have in the experiment, right, the area is such that other peaks are much smaller, okay? So these three are the most important ones. So what are the time scales, right? So there are immediately, just if you look at this, you have two time scales. The first one, right, is associated to the energy difference between those two peaks. Okay, that will leave, right? So if all the particles were really not broad but at a peak, right, this could lead to oscillation. It's like a two-level system in which one level is degenerate. So this is the first time scale. And you see that time scale is set just by the momentum of the peak, this k square, right? Now you can ask, is there anything happening in the experiment in that time scale? Yes, there are two things happening. So if you look at the density distribution, it exhibits oscillation with that precise time scale. And if you look at the momentum distribution, these are exactly, this is the time scale of those oscillations that the experiment had. Okay, you remember I told you that there are these wiggles that are real. So these are precisely that, this is this time scale. Okay, so you can see it in here, notice, right? So what is it that I'm doing here? I'm solving this quench for different initial state with different Fermi energies, right? Sorry, the same Fermi energy, but different momentum K. So if you look at the time scaling here, they are different, right? But when I rescale by this time, right, which is what is done in here, you see that you get exactly the same time. Okay, so the message from this is that there are oscillations that happen in this time scale, which is fully determined by this K. Okay, nothing else than the mass of the particles. Good, so that we call the hydrodynamization coherence time. And this is going to relate now to heavy ion collision, this and the next. Right, what is the other time scale? The other time scale has to do with the fact that not only do we have oscillations, right, set by this energy difference, but we also have oscillations set by the energy difference in here and here and in here. So there is a width, right? There is a width of energy difference that you will have. And we know what happens when you have many energy difference entering in the dynamics, right? Dephasing will happen. So that's the other time scale, right, which is associated with the bandwidth of this state, okay? Because we have this that have a finite width and a finite difference. So that width you can calculate is proportional to K and the Fermi energy. well, that determines the prethermalization time or the equilibration time. And you can see it in here. So you can, for example, calculate what is the area difference in between the time evolving. This F is the momentum distribution function at some evolution time, and the equilibrated, right, GGE or time average. And if you calculate the difference and plot it as a function of the evolution time, you get that there is an exponential decay, right? And now, again, and here I fix K and I change the Fermi energy. So I study the state with different Fermi energies. You see they all collapse, okay? When I rescale the evolution time by this dephasing time. Okay, so that's the second time scale, and it's a short time scale, right? So you see this time scale, and that's why these are like so interesting, because they depend on a microscopic parameter, this one, right? The Fermi energy, that depends on your state, and a completely external parameter determined by your experiment, by this K, right? The other one, this one, is fully determined by K, right? There is no microscopic parameter there of your initial state. It's only the mass in there. Good, there is a question, yes. So when you superpose many oscillations at different frequencies. Yeah, then what happened? They dephase. Right, I mean, if you have just one frequency, right, perfect oscillation, right? You have many frequencies, right, they dephase. Right, so that's the idea, right? So it's all unitary evolution, right? There is no, right, external noise, nothing, right? So it is all because you have those different frequencies. Okay? Good. So, which is the parameter? Oh, this is something that you can fit, right? That's determined by the slope. Right, okay, yeah, that's why I was telling you, apologies for this, we changed notation in between papers. So this paper used one notation and the other one. The B is the area of the pulse. Right, so that's why this is so great, right? Because we know that the experimental pulse has a width and a height, and it gives an area, right? And now you can ask, well, do the results depend on whether it takes longer or higher and so on? In this regime, what I'm telling you, it only depends on the area, okay? So fortunately, we call the area A in one paper and B in the other. But these two, okay, and thank you for it, is completely different from this B, okay? This B is just a fitting parameter for the slope. Good, other questions? Yeah, which theta F, yeah, that's the Fermi energy. So is this width? Good. So this is the theta F. It doesn't show up, right? The important thing is that, remember, I was just telling you, because that other energy scales about this difference, okay? It doesn't depend. It's like even if your Fermi energy would go to zero, you would still the oscillations. The Fermi energy controls the phasing. Okay, now let me show you the amazing thing, which is when you go to the heavy ion collisions, right? So will this be able to tell us anything about heavy ions? Now, let me just bring a picture to you so that you see how interesting is the experimental state, okay? So you see in the experimental state, you have the Bose gas, and after you apply the pulse, overlapping in that Bose gas, right? I already mentioned, you have zero momentum particles, and then you have the ones that are moving out, right? This is actually very similar to what you have right after the two heavy ions have fully overlapped with each other. Okay, in that region, you have particles moving in one direction, particles in the other one, and you have the quark-gluon plasma forming. So it's really amazing that these cold atoms, by applying the pulses, they can generate a state that has that property, right? This is very different from throwing against each other two clouds, right? Because two clouds, right, as they start overlapping, you get interaction and so on. So there will be other time scales. You won't be able to see this. So this is really, the two clouds are overlap and you have the particles moving out. Very similar to that in the experiment. So now let me just tell you briefly about these heavy ion collisions, right? So, and I'm going to focus, there are, of course, you know, two big accelerators. So let me focus on the slowest one, this, the RIC, okay? So the gamma, this gamma, not the linear parameter, right? That's the gamma factor in relativity here. So this is of the order of 100, and there was this question about that time scale. So the diameters of this nuclei is about 14 femtometers. So the time scale in which they overlap is 0.1 femtometer divided by c. Okay, so this is shorter than 1 femtometer by c. So that's something that happens after they overlap. So now this is the leap of faith. Good. So these systems are clearly very far from integrable, right? Very, very complicated systems. But now we are looking at something that happens in a very, very short time scale, right? Very short time, the shortest. Huh? So we don't know, but we can assume that there is some underlying quasi-particle description, right? These quasi-particles are not long-lived, but they live enough to play a role at that very short time scale. Okay? So that's the assumption that I'm going to make, right? In integrable models, they infinitely long-lived. Non-integrable models, they don't exist, but maybe at very short times in non-integrable models, they exist. Let's take this leap of faith and say, like, there are quasi-particles, okay? And you see their momentum, right, is determined by the gamma factor, right? So you have these two guys coming, and then you have zero momentum, right, which is that quark gluon plasma that is being left behind, right? So we don't know the mass of the quasi-particles, but if we would know it, then we would know what these momenta are. The other thing that we need is the width of the peaks. We also don't know the width of the peaks, but we know quantum mechanics. And we can bound the width because we know the size, right? The size. So we can use the uncertainty principle and say, well, the size in the position space-time, the uncertainty should be greater or equal to h bar over 2, right? D over gamma is the size. So we can bound this. That's all I'm going to put in the calculation.
Yeah,
there is a
maybe
question?
just one comment.
Yes.
Yeah. So as we know, the QCD is asymptotically free.
Yes.
So at very high energies, you may expect quasi-particle description.
Right.
However, if I remember right, the effective temperature of this RIC, this QGP, is near the TC.
Right. And
so you shouldn't expect free parton.
That's correct. That's totally correct. As a matter of fact, the hydrodynamics description is very viscous. So it's really very strongly correlated. So this is not asymptotically free. Okay. So what I'm saying is, it's not this free quasi-particle. These are not the free quarks. These are not the current quarks. Okay. These are other sophisticated objects that live for very short time, enough for us to make this assumption. Indeed, this is very strongly interacting. By no means I'm claiming that this is the asymptotically free quasi-particles, okay? Good, so now with this, we can go and say like, okay, this is the expression I had written to you, right? And we don't know the masses, right? We don't know the masses, but we can say, well, the quasi-particle masses may be between the asymptotically free quark masses and the actually constituent quark masses. And I'm here actually citing my undergraduate papers. I was doing QCD back then and thinking about these problems. So it's really fun to come back and think about it. So if you plug these masses, right, you get that these coherence times, you see, go too short, right? We know it doesn't make sense if it's shorter than this, and it can be large, okay, like 4 femtometers divided by C. Okay, so this, but we don't know, right? Because we don't know the mass of the quasi-particle. The important thing is what happens for the damping time. And the important thing for the damping time is actually doesn't depend on the masses because it's ultra relativistic. So you see the damping time only depends on the diameter of the ions and this gamma. And you see miraculously comes to exactly that time. Now, of course, look, even if it could have been 1,000, maybe this is correct, right? Because we don't know the prefactor, but it's pretty amazing that we just put the prefactors and we get exactly that time. So anyway, so that at least that gives us, from our perspective, a qualitative picture for where the time scale comes from. Well, the time scale really comes from these velocities that the ions have, okay? And it's a pure quantum effect. And then, of course, if we were able to know what this width is, we would remove this diameter of the ions from there. Good. So that's the journey through contact interactions, right? So I was telling you, we've learned stuff about what happens at very long times. We have learned very interesting things happen at very short times that potentially could be useful for understanding experiments with non-integrable model heavy ion collision and what have you. So at this point, I can take questions, right? So about this, yeah.
So is this a bit? Would this suggest perhaps that there is some model that is not very far from quarks and gluons, but modified a bit
Yes.
so that it is integrable? So that your system is almost integrable.
But again, these we only need at very short times.
Yeah.
Indeed, at very short times, yes. Yeah. I would say that would be kind of the something that one could try to build. Right? It's the same as the cold atoms. In the end, nothing is integrable, right? And we've been discussing in the trap is non-integrable. It's all about the time scales. Right? So the linear gas in the trap, non-integrable, right? If you wait infinitely long, it will thermalize, right? But for the time scale of the experiments, we can do it as integrable. In this case, indeed, that suggests that there could be an integrable model that is valid at very short times and could describe that. Good. Other questions? Good. So, how do you mean? Yeah, it's a three-dimensional system and so on, yes.
So it's a 3 dimensions, even though it's...
Yeah, it's a three-dimensional system because what happens is that the sheets overlap, right? I mean, of course, the dynamics that we are studying is in one direction, right? But the sheets overlap and then you get a quark-gluon plasma that is a three-dimensional system. But you see in here, right, in this picture, like in this, the dimensionality doesn't enter, right? All we need, right? Because all we need is 2 time scales, right? And that's all we are using in here, okay? So if we have those 2 time scales, that we can apply to any system. Okay, good. Any other question? Excellent. So this is all for the contact interactions. Now you can ask, okay, so let me just make a comment in here that I think some of you have also doing like classical simulations with hard rods have like found the hard way is that, once you put this system in a good approximation harmonic trap is actually a Gaussian trap. In the experiments, for the times that they can measure, they just don't see non-integrability. Okay, so at some point they lose the system because of losses and heating and so on, but they just don't see integrability. So it's contrary to the intuition maybe 20 years ago that integrable models are super fine-tuned and you will never see them in nature, right? Actually, they have to work hard to see non-integrability in this setup. Okay. So that's not the same as what happens if you have dipolar interactions. And you heard about dipolar interaction yesterday. And you actually heard about this paper in particular. So with dipolar interactions, and that's in the group of Ben left, they can do exactly the same experiment that Dave Weiss did with this Newton's cradle. And now this, I'm actually showing you the initial distribution, momentum distribution function that they create by applying what is called a Newton's cradle sequence, which is 2 pulses, which are perfectly timed in a way to completely kill the central momentum peak. You see, they start with a momentum distribution function actually that looked like this, and they let it evolve, right? And if you are in 3 dimensions, okay, I'm going to tell you about these angles later, but if you are in 3 dimensions, you know, it takes a few oscillations periods to get something that is perfectly thermal. Okay, everyone sees that? So, and this is 100 milliseconds. So if you go now to 1 dimension, this is, you do the same in 1 dimension, you see that in that time, you get exactly what I had shown you that Dave Weiss got, 20 years ago. You get this distribution that is non-thermal. Now, this is actually pretty amazing. Let me tell you why this is pretty amazing. Because in 3 dimensions, the gas is very dilute. Okay, so you have to think about this. It's a very dilute gas, right? In which atoms collide with each other once in a while, and you get this equilibration. Now you take the same gas and load it in 1 dimension. What is it that you have done? You've reduced the available space for the atoms tremendously, right? So something that occupies space now is all in these lines, right? So they are colliding, many more times in this gas than in this gas, yet, right? It doesn't, on the same time, it doesn't equilibrate. Good, so there was a question, yes.
I seem to remember a paper by, I think, Kinoshita et al.
That's the paper, that's the one that I'm talking about.
That's the one you, so there I seem to remember that the 2 pulses get separated again, and it's like a periodic thing, I mean, in 1D.
Right. Okay, good.
Get separated again.
Okay, good. So let's come back to this. These plots, right, are in momentum space. Okay, this is the momentum distribution function. Okay, and indeed, at very short times, right, in here you don't see it. So there are some coherent oscillations, right? That's what you are remembering, right? And then they decay, but they equilibrate. Okay, and this is what is happening in here. So I show you. So this Kinoshita paper is the paper I showed you before with Dave Weiss at the very beginning. So I can just very quickly go there so that you see. So this is what you have in mind. It's just that I am showing. This is the paper that you have in right. So, but this is after it equilibrates. What you are thinking about is the very short time dynamics. Okay, and in here is showing every period, so you don't see the intermediate oscillation in there. Okay, so good. Yeah, that's okay. So here you see that after every period. Good. So, and this is very similar to what I just showed you before. It's just the scale is smaller, right? So now in the experiments, Ben does have a big advantage, is that he can rotate, he has a magnetic field, he can rotate it, he can control the strength of these dipolar interactions. So and now you see in here what happens if starting at this point, so you see this is the starting point. So essentially, he always prepares the same initial state. That is very important, right? So we prepare this state, and from there, then rotate the field and evolve with different rotated fields. And now what you see is that by doing that, he can control the time that it takes for the system to essentially now not only equilibrate to the local, right, but to thermalize, because you see now it's the full distribution, it's like this Gaussian. So you see that you can control by changing the angle, you can control this time, right? And you can, again, do exactly what I showed you before in the numerical calculation, compute the difference between the time evolving distribution and the equilibrium one. And you get plots, actually I should say that, that this is a setup that now has also been studied within Generalized Hydrodynamics, and one obtains similar relaxation times. So this is the kind of thing that happens, right? When you study that difference, right? So this difference is here. So you see some very fast dynamics, right? And some very slow dynamics. Okay, and you can look at this for different angles and get some rate And you see that the rate, you see it increases as you change this angle. And at that point, we did some very simple estimate. We say like, oh, it's consistent with Fermi-Golden rule. And now I think using GHD, one can be more quantitative about these rates. So, but it turns out that this also happens, right? If you look at really strongly interacting spin models, like for example, the XXC model that was mentioned yesterday many times, the spin 1/2 XXC model, you can break integrability with next near interactions and hopping, or XX and XY, and then this one is what I call the Z. So, and you see that there are rates, and again, consistent with Fermi-Golden rule. As a matter of fact, this is something that happens even if you have a non-integrable system if you break a conservation law. So as it turns out, this slide was, essentially an entire talk on that meeting in 2019 that I gave. So what is the important thing is that when you break a conservation law, even if the model is non-integrable, you are going to get this prethermalization, and you can get the rate through Fermi-Golden rule. Okay, so and this is showing in here for a model that a spin model, the rate as a function of G, and then we do a numerical time evolution, and we do Fermi-Golden rule, and you see perfectly here. So what is it that we can learn in here is that the rates, right, can be very small, right? Though these thermalization times can be very large. And everything I'm going to be showing you past this slide is going to be at much shorter times than the onset of thermalization, okay? Even though there is dipolar interaction, okay? Good, so then now we're going to look at these models with dipolar interaction at very short times, and we wanted to understand the effect of the dipolar interactions. So a few of these things you already saw yesterday. So this is like a Lieb-Liniger model with this dipolar term, which within this single mode approximation looks like this. I think you saw this yesterday. It has a contact part, it has this long range part. And of course, this makes the model non-integrable, and we don't want to deal with that. So essentially all we do is we integrate all this and put it in the contact. So the way we're going to model the system is the dipolar interactions modify, right, the one-dimensional contact interaction, and I'm going to be showing you results for calculations on this model, in which this G1D depends, right, on the 3D, the one that comes from the 3D scattering length, and this dipolar part. Okay. That's the model that I'm going to be looking at.
And does it work? Yes. And how much is controlled this approximation?
How much is?
How much is controlled the approximation?
Yeah, this is completely uncontrolled, yes.
But couldn't
So,
just
which approximation? Single mode approximation or the approximation we are doing here?
the stuff that the point interaction becomes a local delta that is just normalizing Bringer. Now I think below G1D is equal to G1D.
This one, this
Yeah.
in here,
Yeah.
yeah. This is completely uncontrolled. This is for us a way to account for the dipolar interaction in the as a contact interaction.
But couldn't you just maybe even numerically solve the one-dimensional system and see if dipolar plus delta gives you a...
One could. But this, remember, right? I mean, for these calculations, right? Again, we are simulating 10,000 tubes. And so yeah.
I just understand how the long-range interaction is changing the two-body scattering. Okay, I'm not talking about the full simulation, just how close it is to the Lieb-Liniger.
Right. I mean, I think you could do that. I think Jacopo has done this for the right with the.
The analysis is done by looking at the typical length of the bipolar, and you compare it with the typical length of the scattering shift. And if it's much larger, it's not. And if
no, the fact that there's a local interaction is fine, but it could be momentum dependent because it's not strictly speaking a delta. So different momenta see different interactions.
Right. I mean, I think like a careful analysis could potentially be done. That I agree. But anyway, we had like the experimental uncertainties were so large and so on
Okay.
that we didn't care about it. Indeed, at this point, it's on control.
Okay.
Okay.
Thank you.
No,
But-
but it's true
yeah.
that, but there's, I mean, there is a typical momentum in that's the point. It's a typical moment. At least that's from what
No,
I
but
understand.
Jacopo, I mean, I think the other thing is, you know, you can also think about where do you cut off the integral of what you put in the contact, right? Which, I mean, in here we didn't. So, I mean, there is a spectrum of things that you can do, right? I mean, if you forget the exact calculation, right? You can just forget completely about the dipolar interaction, right? You can try to put part of it, right? Only part of it in the contact. We just put everything, and that's on control. That's I think Jacopo has in mind splitting it and then putting part of it according to the length inside the contact and some other part is long range.
But I mean, you don't really need to split. At the moment you know the characteristic length, then you can compare with the scattering shift at that momentum, that typical momentum. But then you're right, of course, there will be momentum where the
Yeah,
scattering
it could
shift
be
will
that the
different.
momentum dependent
Yes.
scattering shift is not given by just the
Yeah,
boson
yeah.
with the normalized scarping. So you can still model the interactions it was local, but with a different momentum
Yeah,
dependence.
we can talk about that later. We didn't do it, and you will see it's anyway. Yeah,
Yeah,
not make a
I know the
difference.
paper, the agreement is very good, but I was
Right.
just wondering if
Right.
have been done
Good.
such analysis. Thank you.
Okay, good. So now let me tell you briefly, because that's something that you know, maybe it's not apparent from the previous discussion about experiments that you know, modeling accurately what's happening in the experiment is complicated when you don't know, when the experimentalist cannot tell you exactly what is the distribution of atoms in the tubes. Okay, so then you have to theoretically model this. So let me just tell you briefly so that you have an idea what kind of modeling goes behind those calculations, right? So you see they have a 3D gas, right? And they end up with a 1D gas, right? At some depth. And the question is, how do you model that initial state? So this is the kind of thing that we do, okay? So what we say is like initially you have this 3-dimensional system, right? Which complicated, we don't know what it is. But at some depth of the 2D lattice, it decouples into 1D systems. Okay, starting at that point, we can do better answer to describe the system. And what we don't know is what is the temperature of the gases. We assume that they are in thermal equilibrium, nor the density. So these are essentially the temperature, and this decoupling depth are parameters that we have to fit. Okay, so then we determine the number of atoms and the entropies. And then, right after that, they decouple. And then we assume that the rest of the loading into the deeper lattice is adiabatic. So, you know, we have to really evolve for the tubes, keep the entropy fixed, right? And then we get different temperatures of the tube. And then we use this compared to the experiment to fit these two parameters, right? This lattice depth at the temperature. Good, so that's what goes behind that. And now in the case of Ben's experiment, so these are the kind of momentum distribution functions that he gets and the ones in the simulation. So you see, after we fit the parameters, they are well described. The rapidity is not so well. And in here, this is something that we need to work more to understand, okay? So, but you see now, right? Like if you look at the error as a function of the temperature, there is a dip, and that's the temperature that we take. Okay, so this is, you see now, if you were asking yourself, well, how close to the Thom-Girardot gas can they get? So they can get to this gamma of hundreds. Okay, so this ratio between G and the density times the constant and so on. So this is what happens if they go to a lower gamma. And in here, you see we have a larger disagreement between the theory and experiment. And, but you know, it's reasonably good. So now I can tell you, like at this we know now, not at that time. So we just posted something of where we believe all this comes. And we believe all this comes from non-thermal effects. Okay, so these systems are one-dimensional. We are assuming that they are characterized by a temperature, but they probably are not. Okay, good. So now comes why is it that we wanted to put the the dipolar interaction in the contact, because in the experiments they can fix the angle, let's say, and change gamma, and then at any given gamma they can also change the angles, and they see that this dipolar interaction have an effect both on the density, on the momentum distribution function, and on the rapidities. And then we can do now the equilibrium calculation and see that qualitatively we describe what happens in the experiment. Now, these calculations are quantitative really only when gamma is large. Okay, so for small gamma, we have things that we need to figure out. So this is going to be somehow the starting point for the other calculations, the dynamics. Okay. So good. So this was just to characterize the equilibrium. Now I'm going to tell you the exciting thing, right? So what is it that is exciting that you can do with these gases that is kind of difficult to wrap our heads around like that. So what they can do is, and this was done in this paper for the first time, they can use Feshbach resonances to change the sign of the contact interaction from repulsive to attractive. Okay, now the attractive gas is not thermodynamically stable, right? So what they can do is they can, create a Tongs-Girardot gas at a very high gamma and quickly go to the attractive side and create a highly excited, stable state of attractive bosons. Okay, so that's what they did. This is showing the energy as a function of this parameter gamma, right? This is what I was showing you before, this regime in here in which the interactions are repulsive, but they can cross this and go to attractive interactions. I'm going to show you results that are obtained at these different points, right? So this is repulsive, this is very large but negative attractive interaction. This is the most interesting point, and here is weak. Not this is a log scale, okay? And since I know that you are not going to remember the colors, so I'm just going to plot these relative two particle wave functions just for you to keep in mind. This is repulsive, TG, the attractive scar, and this is weakly interacting, okay? So whenever you see one of those plots, then you know where this is. Good, so now I can show you what now the comparison, right, for this Tongs-Girardot, the comparison between the theory and the experiment, both for the momentum distribution function and the rapidity, are very close. Right, so in these experiments, right, no. So potentially some part of the DDI is playing a role in stabilizing those car states. But that's it. Okay, so right, again, so it's this state, right? It's a very highly excited state of the attractive side that you could call it a scar state. It's like an atypical state at that energy, right? It's a state without strings. Okay. Well, I mean, it depends what you call the supertongs. I mean, the supertongs, I mean, sometimes people call it like gamma minus infinity, right? So that's, I'm sorry, like I'm trying to avoid the terminology and so on. So that's why I would say repulsive, like very strongly attractive, right? And then attractive in the same footing, and weakly attractive. Okay. And again, everything I'm going to show you is on time scales much shorter than the time scale at which the dipolar interaction is going to break integrability. Okay, no role of the dipolar interaction. Good, so essentially this is just to show you that we look at the equilibrium state for the different cases and do the theory, and we kind of describe reasonably well the rapidity distribution. Now, I should tell you in here that there is an important caveat to this regime we can simulate with this TG theory I was showing you. That's why I spent so much time, and you can get the momentum distribution and the rapidity. Right? In this regime of the scar state, we can get the rapidities, but we don't know what the momentum distribution functions are. And as a matter of fact, that's something that with Jerome, we are thinking about, developing a way to describe momentum distribution function of these states. That's why in here, in this regime, there are no momentum distribution function from the theory, okay? Good. So now we can do dynamics, yes. In the attractive side, I think we just feed the temperature so that, yes, that's correct. That's why, again, these are the caveats, and that's why we know, and I was telling you that the fact that we are assuming that it's thermal will have an effect on the result. Oh, you want to? Oh, the things.
Couldn't you just run the GHD, like you are changing interaction, you can do that and describe it with the evolving state rather than being thermal.
No, it's about the initial state, right? The
Yeah, but-
initial state is the one that we don't know.
No, okay, sure. And then what do you do to describe the change in the attractive phase and the scarce state?
Right. Once we know the initial state, we can do GHD. What we don't know is the initial state, right? So let me come back, right? You have a 3D Bose gas, right? You load it in one dimension. So this is something we cannot simulate.
But
Right?
I'm just curious, which GHD do you run?
How do you mean which GHD?
You start in the repulsive phase, you are changing interaction, you are...
No, exactly. Okay. Yeah.
So
No,
the
that's
scarce state
not
doesn't work
correct,
like
not
that?
correct, not correct. Okay, guys, so let me step back. The GHD is run at fixed interaction, okay, and it's just going to be a trap quench. So we have an initial state that we assume that is a thermal state, right? We have the rapidity distribution, right, with attractive interactions, no strings, and then we run dynamics after we quench the trap.
So you're assuming that in the scarce state, you have a sort of thermal state where
That
you
is
truncate
correct.
the population to just one string.
That is correct. That is exactly what we are doing.
Okay.
Okay, other questions or no? Thank you for that question. But we don't do any dynamics to describe that initial state. It's an assumption. Good. Okay, but the TG gas, right, is something that we can solve. And in here now I'm showing you, right, so the momentum distribution function and the rapidity distribution, the evolution both, right, in the experiment and in the theory, and you see that they are reasonably well described. Now, this gas has a very interesting feature in the dynamics. So, and this feature, which actually, figured out by Dima Gangar and Minguzi in this old paper. So the feature is as follows. So very unintuitive. So look at this. You have your Bose gas, right? That less TG gas. You change the trap. You make it stronger. Okay. So what's gonna happen with the momentum distribution function of the gas at Isabel, right? So it starts very sharp and it will broaden. But remarkably, as the gas gets to maximal compression, the momentum distribution narrows. Okay, this is what is happening in here. And you see it in here when you look at the full width and maximum as a function of time, right? At half the period, you see that this width narrows. And then as the gas continues, then it broadens again. Okay, and then it goes to the initial distribution. Well, this physics that is known from the repulsive side, they can see it in the very strongly attractive. Okay, so that's, and this is all happening, remember, in very short time scales compared to the time scale of thermalization introduced by the DDI. Okay, just one oscillation period. Good, so this is physics that we knew. Actually, this is something that we had seen in the experiments with Dave Weiss. So now the big question is what happens, right, when you go to that attractive state, right, that state that is unstable. So good, so let me, here now you see is everything about rapidity distribution. We have no data for the, no theoretical prediction for the momentum distribution function. So if you look at the rapidity distributions, right, it doesn't matter whether you have repulsive state, you have that attractive, right, that I call a scarce state or weakly interacting, you see it's always more or less the same. Okay, the rapidity distribution broadens and so on. So it looks the same. Now, the remarkable thing happens when you look at momentum distribution functions and energy. So this is now the total, okay, energy per atom, right? How do you get the total energy? You integrate this rapidity distribution, right, with this theta square that you were seeing yesterday in the talk. So by Ben, so you get that this is how they evolve in the for the three regimes. Now, this is what is surprising, okay? So this is where the interesting thing happens. You can look at the kinetic energy. In the experiments, they measure kinetic energy by time of flight, getting momentum distribution function and integrating it. Okay, so this in here is the repulsive case. Okay, so let's just look at the experimental data so that you see what the first thing they saw and that led to something interesting. So you see, if they look at the repulsive case, it's very similar to what I showed you in here, right? Good. So if you look at the repulsive case, it's very similar. It has a dip, right? Like, do you remember where that dip comes from? It comes from maximal compression, kinetic energy becoming interaction energy, right? Now, if they go to the attractive case, they see the same, right? But that makes no sense, right? Because the interaction is attractive. As a matter of fact, indeed, this is the GHD simulation. The GHD simulation tells you that instead of seeing a minimum, you should see a maximum, right? It's different. So you see the GHD simulation in the repulsive shows you what happens in the experiment. Like if you go to the weakly interacting, then again, the experiment and the theory agree. So you see, if you look at this, right? And if you only look at this, you could conclude that there is a violation of the energy in the experiment and they make big news about it and so on. But then you have to think a bit more about it, right? So in particular, you see that away from that point, the GHD and the experiment agree with each other, right? So, and you see before and after this happens, right? And that's why it would be great now to have a theory to understand these dynamics of the momentum distribution function to understand what is happening in here, right? But we actually have a pretty good idea of what happens. So let me also show you something that is important, which is if you look at the momentum distribution function of the repulsive state and the attractive one, right? You see at low momentum, right? And that's already telling us a bit of where the solution is going to come. It's very similar, right? So you couldn't tell apart the attractive and repulsive gas by the low momentum part. Okay? You cannot. However, right, and this is in the experiment, remember, we don't have a theory for this. What they see is like an incredible difference with the tails. Now, again, remember, this is, I'm sorry, this is because the experimentalist, right? Remember, it's a time of flight. So again, everything in the experiments is momentum distribution function, but they take a picture and they call it density distribution. But this is a time of flight momentum distribution function. Okay, so good. So this is the momentum distribution function. And you see that, that essentially the repulsive and the attractive state, these two states, very similar at low momentum, and at high momentum is very different. So you can see how many atoms are in the tail and the fraction of the energy that they will have is very different. Okay, so that's essentially the answer to what is happening, right? So in this current state, and it would be nice to get a theoretical description. When the gas compresses close to the maximal compression point, right? Most of the distribution looks like the repulsive case, but then very long tails emerge in the gas, okay? And these tails have very few atoms, but they had humongous amount of energy in there. So in the experiments, they miss these atoms, right? They are in the noise. They cannot see that energy. So after we figured this out, so they really did a lot of experimental measurements to reduce the noise. And after doing all the work, they could see, right, that there is no dip in the at maximal compression. So this is the repulsive and this is the attractive, right? But they are still far from the actual theoretical prediction. So they are missing kinetic energy that they just don't see. It's in the noise. They cannot detect it. Okay. So. How do you mean the error bars? Well, it's just that this error bar, yeah, is not telling you the entire story. Okay, so let me. The thing is that now you see the error bar is with respect to the noise. They have a noise that is independent of the experiment that they have to find. Okay, there is a noise floor, and then they subtract from that noise floor for different shots and so on. So there is indeed a complication, right, that you have in these experiments. And indeed, if the error bars in here don't get you, it tells you that there is something in the errors that they are not accounting for. So that if that's the point, that's true. Yeah.
Okay, this works. Just a suggestion, maybe it's a bit wild, like with Christopher look at bound states and what they were doing essentially were like particles with not many of them, but with huge kinetic energy. Since here you have, in any case, because of the polar some weak integrability breaking, it could be that some atoms are forming bound states and these then are contributing a lot like kinetic energy.
We know that it's not the case because you see first, right, the total energy is perfectly, the rapidity distribution, right? They measure rapidity distribution. The total energy that they get from that is exactly the one we get theoretically. And that's the good thing about having different tools to look at the experimental results. So you see, what is important now to keep in mind is that in the experiment to measure this and to measure this, they do two completely different experiments. Okay, the dynamics is the same, right? So you see, they quench, there is sloshing, right? Now to measure rapidity, they turn off the trap and expand in one dimension, right? This allows them to get this, which is perfect agreement with the theory, without bound state and without anything, right? And then these, they do differently, right? So after, some time, they do three-dimensional expansion and they measure momentum distribution function. There is no question in our minds that the disagreement comes from the fact that there are high momentum tails and they cannot measure it. It's not about the description of the state. Okay? So the description of the state you see here is just perfect. Right? We are not missing anything in the GHD when you look at the total energy.
So it's just a momentum tail, in the momentum distribution, there's some tails that experiment doesn't see, and so it cannot account for the energy.
That's correct. That's our belief, but hopefully we can do a theory sometime soon and see it. And it only happens, right? The other thing you see is not at all times, and that's why it's different from what you are doing. It's not happening in the initial state. It's happening really at maximal compression. Everything else we can account for. Okay? It's a dynamical process. It's something that happens when the system gets to this maximal compression point. Good.
Okay, thank you.
Okay, so with that, let me just finish. Let me thank my collaborators, some of whom are here. Jerome is here. Saran didn't make it. Thank the NSF for their support, and thank you for your attention. Okay, what?
Thank you for the talk. I think I didn't understand the physics behind the dynamical fermionization.
Right, let's talk about this physics. I mean, it's very interesting, right? So it's a very, so let me tell you what is happening. So I'm gonna put it in there so that while I explain, you can see it again and again. So, so maybe, I mean, are you familiar with the time of flight? Is that the picture that you have? So if you take the system, right, and you turn off interactions, right, and let it expand, right, then momentum is conserved, right? The momentum distribution function will not change. These are free particles, right? That's what we learned in quantum 1, so it doesn't change, right? That's what experimentalists do to measure momentum distribution function. They turn off everything, let it expand, right? This dynamics is different, right? What is happening in here is you have these bosons that are interacting in one dimension, right? And then you let them expand in the presence of interactions. Now, you see, now the momentum of the bosons is not conserved because they interact, right? But these rapidity distributions a la GHD, which are obtained for the homogeneous gas, are conserved, right? And now what is happening is that as the bosons expand, right, they are going kind of asymptotically free. Their momentum, the real momentum distribution function, is mapping into those rapidity distributions. Okay, so that's the way you can understand it. And you can see that it cannot be other way, right? Because a very long times, right? So you know that the density distribution, right, is fully determined by the initial momentum distribution function, right? And it's the same for bosons and fermions. So it must be the fermionic momentum distribution function. So that's another way you can wrap your head around the fact that that's what must happen.
Thank you.
Okay.
I mean, not a conceptual question, but like when in the last part, when you had like you went to the attractive case in the
Yes.
deep linear model, in one of the parameter of gamma, the wave function didn't have a cusp. Why is like?
Oh, it's the attractive. It's the almost non-interacting case.
I see. I mean.
Okay. So you see, so if it's non-interacting, right? So non-interacting in the repulsive side, you get the bosons fully overlap, right? Now you are after you have passed that, right? So you don't have a cusp, but you have a higher curvature. That's why the wave function, and that gives you the higher kinetic energy, but there is no cusp indeed, right?
Thank you.
So it's like a non-interacting, but at that high state, yes. Good. Other questions, yeah.
Thank you very much for interesting talk. And I like to ask about this Rick business, this region. So according to this, your argument, so for short time, they will maybe behave as some non-integrable particles.
Yes.
And then but it means so thermalization is to this GHD rather than conventional hydro. Do you have any comment between this transition from this?
Good. Okay, good. So first, this exactly. So then to what it equilibrates, right? That is the big question. What is it that it equilibrates to? So indeed, if there is something conserved, it's not going to be thermal, right? And this is the other thing that one of these experiments showed, right? Even if you have an integrable model, right, the momentum distribution function can be actually close to thermal. So you see in this case, right? So indeed, you see, this is a very interesting point that it also relates to typicality, right? So in these integrable models, and even though they are integrable and you will not have something that is thermal, you have to work hard to have something that is far from thermal. Okay, this work hard, for example, was this kind of quench and so on. So in the experiment, right, it is possible that even though the dynamics is integrable with these quasi-particles and so on, you end up, right, with a distribution that is close to thermal. But indeed, that part we cannot describe exactly. That's right. Yes, that's a good question. This is a very important point we thought about. Yes.
How about this transverse direction of some momentum distribution? So you're talking this direction. How about some momentum distribution of the opposite direction to this?
Right. I mean, all the theory tells us is about the time scale, right? I mean, we didn't describe anything qualitatively or quantitatively. I mean, we never put a momentum distribution function on it. We have no theory for it. All we have is an understanding of what the time scale is. Okay, we don't know about the distributions and so on. I mean, that you need to put the partons and you need to do a serious calculation. Yeah. It's just a time scale.
Okay, thanks. Thank you very much.
Yeah. Okay.
Hello? Oh, yeah. So earlier you said that the equilibration or the relaxation would only depend on the initial state of the system.
I didn't say only, it will depend strongly on the initial state, yes.
Okay, more than what the system is made of.
It could, yes, depending
Okay.
on the initial state, yes.
Because say you have a system of bosonic gas and then
Yes.
you have a system of fermionic gas, and by relaxation, it's just a collision, collisions and scattering mechanisms.
Again, that depends on the state. You see, it comes back. So if you have a homogeneous state, that statement is true, right? But the state may not be homogeneous. So something else can determine the early stage of your dynamics.
But then again, in a fermionic system, you have a Pauli's exclusion principle.
That's right.
So then collision and relaxation would be much harder than in a bosonic system.
But
no?
again, that's what I'm trying to, you have to come back to that picture of the expanding cloud. It doesn't make a difference whether they are bosons or fermions. They have to hit the boundary and come back to thermalize, right? And if you have a time scale that is about few times L, like the system size, that's it. I mean, it doesn't change whether you have fermions or bosons, right? In the details, it will change. Now, if you have a homogeneous state and you do a quench, then all what you're saying is true, and then you have to do an analysis, right? But yeah, we have to change our mind to that picture of fixed density and things all being determined by microscopic parameters. That is not true in this game.
Okay, thank you.
If not, let's thank the speaker again.
Okay.